All right, I want to tie up some loose ends from my videos on trig and operations. One problem is I didn't cover inverse trig, but I'm going to do that in this video. And I'm also going to talk about one other thing I realized with inverses that makes it really nice to understand. So here's our inverses. And we already went to logarithms a good bit, so I'm not going to go back to those. Some rules extend well from the third one we're going to talk about. So you have positives, then you have, well, not positive, I mean addition. You have multiplication, then you have taking a number to a power. All right. Now, to undo each of these, I'm just going to do it in a light green. You take the negative, subtract. That was a hint. You take the fraction, divide. And this, you root it. Take it to the inverse power. Just root. Yeah. That was a pretty pretty lame foreshadowing. Yeah, I pretty much gave it away. Well, here's the idea. You can think of these in many ways, how they undo each other. Really useful, but this is my favorite, just kind of thought that extends well. And really that's how I like to think of math, just what ideas extend well with other operations. And it's like, whoa, I understand this operation now, because when I think of this early operation that I clearly understand, I can pass it on. And so I just like that kind of manner of teaching. So I'm going to go right into it. So you have addition and subtraction. So you have, I just keep using 5 and 2. I don't want to do that. So let's do 9 and 6. All right, so 9 plus 6. So you can do that by subtracting 6. Yeah, nice. That's established. I think we all get that. But here's the thing we do, and this is the thing I want to establish. We keep these as they are, and we invent a name for them. And the thing I hadn't gone across that I want to in these videos is that these have very similar properties. And this is why. So in order to give these similar properties, otherwise you're just subtracting and you have this other operation that, I don't know, it undoes addition, but it does something similar. Who knows though? Well, this is how to find out. So you have positive. So what you do is you say, okay, maybe I'm not subtracting, but this is just a way of thinking of it. And you've probably seen this one before. You can think of it as adding what we call a negative number. Lots of people like teaching these things like debts. So if you're giving someone debt, you're adding negatives. Or you could just think of it as subtracting. Either one is perfectly valid here. And same thing. So we invent what we call a negative number. So let's try this again with multiplication. So we have 9 times 6. I'm slowly going to turn this into a dot. Then we're going to divide. And I like dividing on bottom. It just makes more sense. But here's why it makes more sense. And it ties perfectly into this. So we could say, okay, we have division. It's not that similar to multiplication. But it is, because let's check this out. We invent something called, and try to guess it for a second. This is what you multiply this by to be the same operation. Well, a fraction. We invent what we call a fraction. And I think fractions are well understood, but this connection between them has always been hazy, and this just clears up the smoke. You're like, whoa, check that out. That's incredible. Just crazy. And honestly, converting it into these systems, it seems weird and almost like useless. But if you see it in these lights, you can treat these numbers as you're allowed to with algebra. And let's do one more, which is these ones. So let's take 9 to the 6th power. That's a big number. 9 to the 6th power. So we can do that by taking the 6th root. And by the way, it would be positive or negative because 6 is an even power, and multiplying things an even number of times gets rid of the negatives, and so it'd have to be plus or minus when you undo it. But for now, we're going to ignore that. Just because that just makes your day. It was fun, but not anymore. Here, I'm going to make it Fruit Loop colored. Yeah, there we go. So the idea here is this would equal 9. However, the other way we could write it, so we understand it, is 9 to the 6. Let's put parentheses around this. Same as taking this to the 1/6 power. And I already said this, but holy moly, it connects well. So this rooting thing is a way to undo powers, and it also is, this is the connection to exponents, because this is the exponent. This is the multiplication. This is the addition. Just different kind of addition. So this is how we transfer ideas, and it's really nice for thinking of algebra. Let's think for a second. So we have fractions, we have negatives, and we have, well, it's still powers. It's still powers. That's what I want to get at there. They can keep things as powers. I'll put a box around that. All right. What else? And you can keep things as logarithms. Logarithms. I actually don't know how to express those as powers. Huh. That's interesting. Good luck if you do. If you can have this extend into logarithms, good on you. I just like this for these three ideas: negatives, fractions, and connecting roots to those inverses. All right, so now the other idea in inverses, and then we'll bring this to trigonometry right after this. So this is the other concept I wanted to cover in inverses that I didn't. Let's just switch pages. Why not? And so the whole notion of an inverse and why it's useful is for this very reason. Let's move this a bit. All right. So here it is. So, by the way, function notation. I'm going to just bring this up. If you're not used to it, don't worry. I'm explaining this right now. If you are, I don't know. I just know I'm going to use it in a second. So this is a simple way to write usually y. We usually write y equals something with x, whatever. And I like f of x. It's almost a personal preference because you can see the input with it. The input here is just x. And you can even plug in functions inside of that. And by the way, function just means you plug in an output, and you only get, you plug in an input. You plug in the input, and you get only one output. If you got anything more than one output, then it wouldn't be a function. And plus, that'd be confusing. If I plugged in 2 into this function, and I got -3 and -5, I'd be confused. Like, how did it pop out multiple numbers? Either way, it just confuses me. And not that math was made to not confuse me, but I'm just showing you that this is an approach to understanding these. So you can just plug in a simple function inside here, or you could just plug in x. All right, so, and by the way we write inverse function, we're going to go over that right now, is we just put a negative up there. You know how, like, we'll go into that, whatever. So let's get right into this, jump right in. So let's say it's equal to, I don't know, 3x plus 2. All right, so this is going to be two-step to rearrange it. So let's just say that x here is equal to hours elapsed. Let's just say hours. So let's say this is, you're paid $3 an hour and you started with $2. This would be a valid equation for that scenario. At 0 hours, you would have the $2 that you started with. All right, and what would the output be? Well, it's the total money you have. So let's just say total cash. All right, the idea of the inverse function over here, though, what f prime of x does is so we have a separate scenario. This is what happens. What you do is you solve for this x term. You put x on by itself and put f of x over here, and then you just switch what x looks like, so it looks like this. You'll see why that's useful in a second. Either way, so you have an inverse function. That would be hours, because you turn this into that inverse. We're going to go into it. And I shouldn't write equals. That's not really, I guess this is the dimensional analysis way to do it. Just put brackets around it. So you're analyzing the dimensions. Either way, so that's in hours. And what else? So that's, oh yeah. And so then you'd output x. And in this term, in this time, our input is total cash. And let's go into where, so we change what x is in these circumstances. So first, let's just do what I was saying. So you have 3x plus 2. This is easier if you have it with y, just because moving letters around, I don't have to write f of x. But either way, y and f of x in this scenario are the same. So we're just going to treat them the same. So 3x plus 2 equals y. Let's make x by itself. So how do you undo this addition? We just went over all this stuff. That's just algebra. So you subtract. Now you subtract this side, so subtract this side, bouncing the scale. All sorts of ways to think about it. So now what we did is, or yeah, you could also think of it as adding a negative, and you can add things both sides. That is why you can add negatives. Just continues on. So these cancel out because plus 2 and minus 2, they're supposed to cancel out. That's how inverse works. So 3x. Now we're going to do one more inverse function in order to finish this job. And it's dividing by 3. Dividing by 3 cancels out the 3. But I'm going to do it the other way. I'm going to do it that fancy way I like talking about it. I'm going to multiply by 1/3. And by the way, one rule about multiplying is you distribute. If you're multiplying by a fraction, you can distribute multiplication. So in that sense, you can distribute division. This confuses a lot of people, but that's why thinking of this in terms of multiplication helps the process. So 1/3 and 3 cancel out, so you get x over here by itself. I keep switching colors. And then you get y, so let's distribute this. So 1/3 times y is 1/3 y, or y over 3. That's nice. And you can just keep it as a fraction. And 2 times 1/3 is 2 over 3. And there you go. You can just keep it as that. And so, if you have a total amount of cash, you can plug that in as y, and it outputs an x. Now we do one small fix. Now that, since x is hours, we're going to invent the inverse function. I don't know why I say invent. I just kind of like that term here. So we do that, and we swap y with x. So we're plugging in x, which would be the total amount of cash we have. Let's use this in a reasonable scenario. All right, so let's say, give me a second. What if I had, I don't know, after some number of hours, we don't know the hours, but we know the function to calculate hours. Let's say I have, and we're saying all this is in dollars. I have, how about, I'm thinking here. How about $14? After how many hours would I have $14? Well, if I plugged in this function, you'd have to rearrange stuff to solve for x. But if I plug in this function, this one, you plug in hours and it outputs, your final result will be, you plug in total cash into x, and your output would be hours. So this is really useful. So now we can calculate hours based on how much money we have. So if you're like sleeping on the job or something, and then, whoa, I have $14, and I know this is the function for it, so you can figure out how many hours elapsed without looking at a clock or anything. Although that this situation probably won't come to you. Just know that it's there. It's there. So you have 14. So let's plug in 14 here. Let's switch colors. So you have 14 divided by 3 minus 2 divided by 3. Luckily, you can, so this for the same reason that you can factor, you can, for the same thing that you can factor multiplication, you can also factor division. So let's get the 3 out of here. So we have, that's 1/3 times 14. Technically, I'm undoing this work right here. So you could have kept this as your answer. Equally valid. Minus 2. All right, 14 minus 2 is 12. And 12 divided by 3, because it's 12 times 1/3, is 4. So 4 hours elapsed. So it must have been 4 hours. That is why I have $14 on my desk, or whatever. So that is the beauty of the inverse function. And let's just finish this up. Let's just keep like 2 colors for now. All right. So now we're going to extend this into, so we did division and all that stuff. Also realize, I didn't even cover this. I kind of wanted to, but just realize that the way we represent, so if we represent, or I meant to cover this, I'm just going to do this really fast. So if we have 5 plus 5, no, 5, minus 5, 3 times, and they're all subtracting, that's -5 times 3. Okay? And that's how you represent it. You put a negative in front of one of these results and you multiply it. So you have a negative multiplication. All right? So that's how you get from here to here. And now what happened? How do you get from division to here? And by the way, I guess this would be subtraction to multiplication, because subtraction relates to multiplication, doesn't relate to division very well. So let's relate this division to powers. So let's say I divide by 5 a bunch of times. So I have 5, let's say 1. So let's start with a fraction. 1/5 divided by 5 divided by 5. All right. So I divide by 5 times. So it's 5 to, divided by it 3 times, I mean. Sorry, I get confused about that. All right. So, but instead of doing it positive, because if I made it positive, then that would be multiplying times 5 3 times. But I didn't do that. I divided, so we make it negative. And that's how you define negative exponents. So if we multiply this times 5, so 5 on the front, this would be the same as 5 to the 1. And you can just add those powers. So you get 5 to the -2, which is 1 over 5 squared, which is 1 over 25. So this result would be equal to 1 over 25, 1/25. All right. Just letting you know. That's all that this stuff is. So just repeated. Yeah. And I imagine roots probably connect somewhere if you did multiple powering, but I'm not going to think of that. You can mess with that on your own. Let's go straight into, this was trig, I don't know, metry. I already spelled that wrong, didn't I? Trigonometry. There you go. That's how you spell trigonometry. Trigonometry. All right, and we're talking about inverse trigonometry. I like that. Inverse. It's just catchy, very catchy. Let's put dashes here because that looks fancy. And so we have our basic functions are sine, and we're not going to use angle, cosine, and tangent. Sine starts at 0 and it continues like that. Cosine starts at 1 and continues like that. Tangent, oh my goodness. If you remember tangent, not super friendly. It just keeps on doing that weird arc thing. Goes all the way from -infinity to +infinity. And starts at 0. So that's 0 point, that's 0 point, that's 0 point. All right, so what inverse trigonometry should do, what inverse functions do, is they basically, is interesting. If you graph any inverse function, like the one we did on this page, yeah, if you actually graph this and then you graph this function and keep the same x, Well, this one would be 3x plus 2, so it would be up 2. And 3, this would be x divided by 3 minus 2/3. It actually looked like this. And this is jetting out from the y-axis. And it just so happens that you're always reflecting over this line, which is y equals x. Try it on your calculator or something. Or that online graphing tool. I think I linked in the last video. So this is the same scenario. When you make up inverse things of these functions. So let's talk about inverse sine for a second. And that way we define inverse sine as just the inverse function of sine. Not too fancy. So it starts at 0. So what we do is we reflect it over this axis. Now remember, functions can only have one output. So when you do it vertically, so this is how you test to make sure it has one output. If you do it vertically, check it out, only has one output for each of these. So if you line up the x to its y value, it only has one y value. Well, what happens when we reverse this? Let's change colors. Let's make it like black. So if you reverse this, kind of, is a little difficult. Kind of does this shape. If you flip it, you can test this for yourself by just drawing this out. Either way, you get a curly. However, if you line it up, this is called the vertical line test. It's useful for thinking of this. Check it out. We'll actually have, this goes on forever, right, when we reflect it. So you're actually going to end up having infinite values for this function. So it's not a function anymore. Using the word function would be wrong. Except the way we define it is we don't care about all this mess because this stuff overlaps. And we don't care about all this mess because this stuff overlaps. So we graph inverse sine as just this. All right, and that's what inverse sine looks like. And if you thought about inverse cosine, cosine starts out, looks like this. So if you took the reflection of it, it would be like, so I'm thinking for a second. I'm pretty sure it looks pretty similar. I'm pretty sure it'll look like this. So just raised up a bit. Man, this is getting overlapped a lot. So that would be inverse sine, and this is how you'd write it. Sine -1 of x. And this would be inverse cosine. Something like this. And it'd be raised up a bit, just because of how we define it. Same width, because it goes between 1 and -1. Cosine also does that, so this will go between -1 on the x-axis and 1 on the x-axis. This will go between -1 and 1. So same width, in a sense. And this would be cosine. I'm pretty sure that's what it looks like. So if sine, you plug in and you get a ratio. If you remember our old ratios, that would be it. This is just how I define the triangle. Y over x, my bad. So you plug in a angle in for this. And by the way, we're talking about different x's here. This was just the x distance. So this would be theta in the context we were talking. So you plug in angle and you output this. So guess what the inverse does? You plug in the ratio and you get one angle. And remember that this angle will be on this line if it's sine. So it'll only give you like the first negative angle. So it could be any variety of angles based off of that. But realize that every point is equally spaced between the one with the exact same value. So you can use that fact to find out the other values pretty easily. So that's the thing about sine. You plug in this ratio into the function and you get this angle. So you can find angles using this. Then you plug in the ratio of this into x. And guess what? You get the angle. And same goes for tangent. And the cool thing about tangent is because tangent goes from -infinity to +infinity, looks like this, going sideways. All right. So if we flip it like over the y-axis like this, then guess what it would be? It'd look like this. It actually has a value for every x. Now, of course, it overlaps because of our knowledge of what it looks like, but we're not allowed to overlap as functions, so we don't do that overlap, and so we just have this one point, and this goes at the very end. I don't know, somewhere in the infinity, we'll get negative pi over 2 here, because pi over 2 is what brings it to infinity, and positive pi over 2 here, because pi over 2, again, is what brings it to infinity. And that's how we define this. That's inverse trigonometry, and that was the other thing I wanted to cover. So just know that this is a limited thing, because if you flip it, it'd technically not be a nice function. We actually do the same thing with square roots. I just want to show that. Square roots, so this would be x squared. Square roots technically would look like this if you inverse it, and that would make sense because you can plug in negative results and get the same result on both sides. However, this would be plus or minus square root. However, then you get the positive and negative square root of your x value, and that's a bit of a problem because you get a positive and negative result. That's not a function. So we usually only do what's called the principal root and keep it positive. Or you can do the negative and keep it negative and just graph out a separate function over it. Either way, so we do this all the time. We just cut off functions and say it's good enough. The last one is you have a circle function. It looks like this, by the way. This is just a circle with length 1. 1 minus x squared. Technically, a full circle would be this, but we cut off because all these points, there's 2 values for one input, so it's a bit of a problem. Alright, that covers it. This video got pretty long, but I think it's very informational and useful for algebra and pretty much any math onward. Thanks for watching.